So last time we stopped at here actually. Stopped at here. So we looked at signed and unsigned numbers, and then some details about logical operations, and then these shift operations. Now what we were left with was to discuss about these conditional operations. So conditional operations are, it's like one of the most important parts in a processor. One of the important operations supported by a processor or a computer. Now, what distinguishes a computer from a simple calculator is its ability to make decisions. So a computer can make decisions with the help of these conditional operations. Now, based on the input data and the values created during computation, different instructions can get executed. So basically, conditional operations are about if conditions and loops. So you all have seen if conditions and loops in C, but you have actually not looked at how they really work under the hood. So we are going to learn how they are done by a computer at an assembly level. So the main idea here is to branch to a labeled instruction if a condition is true. So even like for both the if conditions and loops, you all have seen that there's a condition to satisfy. Like for if condition, if the condition satisfies, it executes a certain code segment in your program, and if it doesn't satisfy that condition, it executes another code segment. Also in loops, you continuously execute a code segment as long as a condition is true. So in all these cases, you have to check whether a condition is satisfied, and if so, you need to execute particular set of instructions. So that is the main idea here. So if the condition does not satisfy, we'll continue sequentially. So now here we come to the real instructions that deals with these conditional branches. So the first instruction that you deal with when it comes to conditional operations is this CMP instruction, compare instruction. So this CMP stands for compare, and it sets the program status register. So there's something called program status register, which actually stores the status of the program based on these comparisons. So with the CMP instruction, what you can do is you can compare values in two different registers, different or the same. So for the compare instruction, the two arguments are reg1. Now here in this example, the two arguments given for this compare instruction are reg1 and reg2. So what it will do is that it will compare the values in these two instruction registers. Now after the so that is just only a comparison. So it compares whether reg1 is equal to reg2, whether reg1 is greater than reg2, whether reg1 is smaller than reg2. All these comparisons it does when the processor executes this compare instruction, CMP instruction. Now by only using this compare instruction, you cannot achieve these conditional branches. So to achieve a conditional branch, you need to have these branch instructions. So the real branch instruction comes next. For example, in this example, we have BEQ L1. Now, what that instruction does is it checks whether the comparison we did just a little while ago says that the two registers compared were equal. BEQ, of course, stands for branch if equal. So it checks whether the comparison we did earlier says the two registers compared were equal. If they were equal, it will branch to this label L1. Now, these labels are new to you. So labels you have not seen yet in assembly, but we'll look at them very soon. Anyway, for now, just remember that it's just a label in the program which points to an instruction. Okay, so L1 is a label that points to an instruction. So you can have as many as labels you want, and then you can name it as you want, name them as you want. So it's a label to a instruction, a label pointing to an instruction. Now, if the comparison said that the two registers compared were equal, it will branch to this label L1. And now this is regarding this example. So basically, if you write it in C way, like in the syntax you use in C, you will see that it's something like this. What it does is, if reg1 is equal to reg2, branch to instruction labeled L1. And now it is just not only this instruction that you have regarding branches. So there are many branch instructions. This is just only one branch instruction. This is about branch equal. So this is branch equal. So it checks whether the comparison said that the registers were equal. The values in registers were equal. But there's another similar branch instruction that checks whether the comparison says the register values were not equal. So for example, now this example is about that. CMP reg1, reg2. With this first instruction, what it does is it compares the values in reg1 and reg2, and it branches to the label L1 if the register values were not equal. The comparison result actually. If the comparison result says that the registers compared were not equal, it will jump to this L1 label in your program. BNE stands for branch if not equal. If reg1 is not equal to reg2, branch to instruction labeled L1. So this is how branches are handled in assembly. So you have written code to achieve similar tasks in C. So you check whether a particular value is equal to something, whether it is not equal to something, and even you have seen that, like, even you have done comparisons like whether a variable is smaller than a particular value or smaller than another variable, whether it is greater than another variable, greater than or equal to another variable. So all these comparisons you have done in C. So they all are done at assembly level with the help of these different branch instructions. So I hope you got a rough idea about what we are discussing, and then we'll when we go into a real example that has these branch instructions, you will understand it better. So things like how labels work, you will understand it better when we go to a real example. And now there's another type of branch. Now what we looked at was conditional branch. So in conditional branch, you check if a particular condition is met. or not. So if that condition is met, you branch to a certain address, a particular address or a label. But there, there's another type of branch which is called unconditional branch. There it does not check whether any condition is met or not. So with these unconditional branches, you can just branch to a label, and it does not check whether certain comparison said this or that. So it does not check any of that. Now, for example, this instruction be exit, what it does is just ask the processor to go to exit label. So exit is another label, just like the label we had in L1, in previous slide L1. So what it says is unconditional jump to instruction labeled exit to instruction labeled L1. Now, yeah, there's a slight mistake here. The sentence should stop at here. Unconditional jump to instruction labeled exit. Right? So it does not check whether a certain condition is met or not. So it just branches. So this is also important when you try to implement things like loops more commonly. Like most often when you try to implement something like a loop in assembly, these unconditional branches become important. So that all these things you will understand when you go for real assembly examples. Now, did you all get some idea, some meaning? You should you should have got a good idea about. If there's any doubt, just interrupt me at any time and ask questions. If you have any doubts, just ask. So doubts regarding the how instructions are labeled and things like that, you will see later. But the main principle behind how conditions are checked and branches are taken, you need to have that idea. Okay, so signed versus unsigned. Now here, now earlier we talked about signed, unsigned numbers. Now here we are talking about signed, unsigned comparisons. So signed comparisons. Now for branch instructions, there are it can check whether a particular register is greater than. Now I'm talking about an example. So with in branch instructions, it has the ability to check whether a particular register value is greater than another register value, considering the sign or not considering the sign. So there's so it has an option, like if you use a particular instruction type, you will consider the sign of the register values being compared. But if you use another type of instruction, branch instruction, you will not consider the sign. So that is like an unsigned comparison. So for example, here we have given sign instructions you can use for sign comparison, and also instructions you can use for unsigned comparison. Examples for sign comparison are things like BGE, BLT, BGT, BLE. So BG stands for branch greater or equal, branch less than, branch greater than, branch lower or equal. And also in unsigned comparisons, you have BHS, BLO, branch higher or the same, branch low or branch lower, branch higher or higher, branch lower or the same. So all these abbreviations, they will come to that later formally. Anyway, these things are there to do either sign comparison or unsigned comparison. So you can choose between them. Now with this example, you will understand it better. Now we talked about comparisons. So CMP instruction is there for comparison. So that is similar, like that is, it is the same for all the branch applications. Like you have to first compare two registers. Now once this comparison is done, it sets this status register, just like I mentioned earlier. So it sets this status register, which says whether the two comparison says one register is greater than something, greater than or equal to the other one, or it is whether it is equal to the other one. So all these status is stored or recorded in that status register once you do the comparison. And based on that state, and then these branch instructions, it looks at the status register and decides what has happened, and then act accordingly. Like depending on the type of the branch the user tries to execute, it looks at different bits or places in the status register. So if it was not clear, maybe I can try to draw a status register and an example status register and explain it better. If it was not clear, you can let me know later. Anyway, this example is about the difference between signed comparisons and unsigned comparisons. Now here you have in R note we have stored 11111 all ones, this number, so 32 ones, and in R1 we have R0 has all ones and R1 has all zeros, and at the end we have only one. So you first do the comparison. You compare R0 and R1, and there we don't specify whether it's a like a signed comparison or unsigned comparison, because the processor does all these comparisons once you execute the CMP instruction, and it sets the status register. Now when you come to the branch instruction, you can choose between whether to do a signed comparison or an unsigned comparison. Now in the first example instruction, what it does is BLO L1, and this BLO is an unsigned branch lower than. So there, what it checks is whether R0 is lower than R1, considering the values as unsigned values. So if they are unsigned, then you think they all are positive numbers. So R0, if you convert it to decimal, thinking that it's an unsigned number, it's going to be this large number, right? Now this large number we already have seen when we talked about unsigned integers. So this is the maximum unsigned integer that you can represent with 32 bits, 4,294,000,000, this number, right? So this of course is larger than this number. This number is just one, right? When you have one at the least significant bit, it's one. So when you do this comparison, it says that like when you do this comparison as two unsigned numbers, this first number of course is larger than the second one. So with this unsigned branch, it checks like it considers these two numbers as unsigned numbers, and therefore this branch is not taken. So what it checks is whether the first operand is lower than the second one, but it is not the case. So we tell we tell it technically that the branch is not taken. So if this condition is true, we say the branch is taken and it branches to this particular L1 address. If the branch is not taken, it does not branch to the label L1. It instead it continues sequentially. So that also you will understand when you go to an example better. And the signed branch, what it does is, like if it checks in the status register related to the signed comparison, like signed lower than comparison. So BLT, here BLT checks whether the two numbers, the first number is lower than the second number, considering their signs. So branch, now if you consider them as signed numbers, now the value stored in this R note is -1. You can apply that. Now this is represented in 2's complement. So you have to consider it as a 2's complement number. And now we definitely know that this is a negative number because this is 1. And then you can apply the logic we discussed that day and go back and see that this is representing -1. So when it does the sign comparison, -1 is smaller than +1. So the branch is taken and it branches to this L2 address. So this is how signed versus unsigned branches work. Here you can see the branch instruction format. Now we already looked at how branch instructions work, and now here it says how how branch instruction is encoded in binary. So in branch instruction format, you have the first 4 bits are for condition. Now you can understand now this condition field actually is used in these branch instructions, conditional operations. In previous places, we did not get a useful work out of this condition field, but here it's getting useful. Okay, so encoding of options for condition field are given here, so that the encoding is based on the type of branch we need to perform. So, and then the next 4 bits are 12 bit, so it's a hard coded value. And then the address. Now this address is important. This address is actually the instruction, the address of the memory location that stores the instruction corresponding to that label. So we looked at labels earlier. So there's no way of a computer understanding these labels as just strings. L1, L2, exit, all these were labels, just labels we had given to them, but there's no way for the computer to understand them as just strings. So those are there for readability, but the labels at the end of the day are going to be resolved into addresses. That is because we are talking about a location of an instruction to be branched. Like when the branch is taken, it has to go to a certain place in the instruction memory and start executing a set of instructions. Now this address field stores this the address of the instruction to be executed if the branch is taken. So that is the use of this address field in branch instructions. And the condition field, you can see the different options you have, different encoding options you have for the condition field. If it is a branch equal, then you have to put 0 here. And if it is a branch not equal, then you have to put 1 here. If it is higher, unsigned, higher, or same, you have to put 2 here. Likewise, you get the idea. So you have all the codes required for both unsigned and signed comparisons. Now you can, the abbreviations we used earlier are tabular, are put in a tabular way manner here as well. So you can, if you are wondering what this BLO meant, if you were wondering what this BLO meant, you can look it up here in the table and you can see it's unsigned lower. So all these different branch options you can encode with this condition field. And now we talked about the address. Now address is the now I hope you have the idea that the instructions are also stored in memory, just like data, but it could be in a separate portion in the memory, of course. not in the same place where data is stored. So it will be stored in a part of the memory. So instructions, the instructions corresponding to the program are going to be encoded in binary, and then they are also going to be stored in the memory. Now, when you are going to execute a particular instruction, you have to load those instructions from that instruction memory, just like you load data from uh, data memory when we were doing memory operations. So with 24-bit address, now we had a field that has only that was 24 bits in size. So with a 24-bit address field, you can address only 2 to the power 24 memory locations, right? So with 2 to the power 24 memory locations, the memory you can have, or the size of the program you can have, is the maximum size of the program you can have is 16 megabytes, because you can jump or branch into locations only within this portion in the memory. So I hope you have the idea that the instruction memory is also similar to the data memories, where you store instructions. So each byte in the instruction memory is also given a unique address. So what this means is that you have the ability to store 2 to the power 24 bytes in the instruction memory. So 2 to the power 24 bytes is 16 megabytes. So 16 megabyte is going to be the largest program you can have in you can run on your target processor. So we have to come up with a solution to solve this problem. Uh, so 16 megabyte is the largest program you can have, but when it comes to a very large program like maybe an OS, even like you don't need to go to that OS level, but maybe there are other programs, even an accounting program could be larger than 16 megabytes. So if the program is larger than 16 megabytes, you will not be able to branch to locations that are outside this 16 megabyte area. So now the solution the designers have come up with is to uh, get something called a branch offset. We have got a question: can't we compare an immediate operand and a register value using CMP? So that you have to actually check in the assembly ARM assembly data sheet or the guide. If it is not supported, I'm actually not very sure about that. So maybe it supports a native instruction, like it has a native instruction to check whether a register value is equal, or like other comparisons you can do it with an immediate operand. That I'm like exactly not sure. So if it is not supported, then you have to load the value to a instruction first, to a register first, and then do the comparison using registers. I hope, like I guess, these things like comparing with immediate operands is supported, I guess, but I'm not really sure. So you can check it up. Now the solution for this problem is to use something called branch offset. So register, we take a register, and we add the branch address we put in this 24 bits to that register value, and then you get the ability to branch to like you actually get the ability to have larger programs, because now you all know that the branches typically are going to branch to locations that are nearby. They don't branch to places like maybe we for example, if it is a loop, you will just branch back uh, 4 instructions back. Maybe if it is like inside the loop, if you have a large code, then it's going to get branched into a faraway location. But anyway, the branch, the amount of branch usually is less than 16 megabytes. So if you have this setup, like if you have a register and if you can add the branch address to that register, then you get the ability to have a larger program which includes branches that go that are away, like one instruction could be away from the place the branch is done, 16 megabytes away from the place the branch is performed. So this will be more clear when we go into an example actually. Now this second point, just ignore that for the moment because there's a small issue there. Now we need to see, like we told that you can have a register and you can add the branch address to that register and get the final branch location you need to branch. Now this register you need to put there, you need to decide that. So that register actually is the program counter. Program counter, have you looked at program counter yet? Program counter, do you have any idea about the program counter? So you need to have like some idea about the program counter. Maybe if you have not covered it, then we'll look into it later in detail. So the program counter here tells the instruction that is currently being executed. So with the program counter, what we say is this is the instruction that we are currently executing. So the address of the current instruction that is being executed now. So it is what this PC tells us basically. So if you have not done it yet, then maybe you can get more details about that later. So conditional branches in loops and if statements branch to a nearby instruction. So that this is like the typical case, generally less than 16 instructions away. So branches are not branching to, branch instructions are not branching to branching far away from the instruction you are executing. So generally it is less than 16 instructions away. Therefore, we can use this principle, PC equals PC plus or minus branch address. So the register we looked at here actually is the PC itself, program counter itself. Now you can add the branch address or the branch target to the program counter and get the final memory location that you need to branch to. So that is the idea here. And all ARM instructions are 4 bytes. So you know that as well because ARM instruction is 32 bits in size. So it is, in other words, it's 4 bytes. So if you you can refer to the number of words to the next instruction instead of the number of bytes. Now I told that the instruction memory is also byte address. So if you want to get to the next instruction, actually you need to add 4 to the address. So something like now if you are going to put the branch offset here just as the number as the difference the gap as the number of bytes, it is going to be a waste because we already know that one instruction is 4 bytes in size. So instead of incrementing the program counter by 4, if you want to branch to the next instruction, instead of incrementing it by 4, you can tell that you need to increment it actually the PC has to be incremented by 4, but in the place where you store the address, you can just store the number of instructions to the branch location instead of just putting the number of bytes. So relative distance increased by 4 times. This thing you can do in hardware. So this also, if it is not very clear, just don't think about it too much if you have not covered this PC and things like that. So for these examples, we will need only the idea about the compare and branch instruction types. So if it was not clear, like if this is not clear, maybe we can spare some more time and discuss about that later, because we have a limited time for tutorial session, so we'll not be able to go into very details about that. So anyway, the details I gave to you is enough if you go ahead and read about it yourself. And we are now gonna look at this example where it tries to compile an if statement. Okay, so now we have this C code. So this one is very important. You have to focus on this because this is really useful. This is how you do it in assembly. So if you want to know how you do branches in assembly, you need to understand this example really well, because for the lab also you need to use these concepts. So now there's this example if statement written in C. So C code is something like this: if I is equal to j, f should be f should be assigned g plus h value, and if it is not, you need to assign f equals g minus h. Now this is a good example for a case where you need to apply branch instructions or conditional operations. So this is an if condition. Now you need to compile this into ARM code. And here we have given the flow chart as well. And now these FG, HIJ values are stored in R0, R1, R2, R3, R4 addresses, registers. And if you look at the compiled ARM code for this if statement, or the code with this statement, you can see it's going to be something like this. Now here we do the, because now we first need to compare the registers that hold that these I and j values. So I and j values are stored in where R3 and R4. So R3 and R4, we need to first perform a comparison to see whether they are equal, not equal, greater than. So things like that you can do with this compare instruction, CMP R3, R4, you can perform it. And then with this BNE instruction, you can do this. So if the two registers we compared were not equal, branch to this else label. So that is what it says. So branch to else, the place in code which has this else label if the two values we compared were not equal. So R3 and R4 are not equal. We can now see. Now check actually. We have not assigned any values to put. We have not actually put any values to R3 and R4. So we cannot say whether they are equal or not. But if they were not equal, then we are asking the program to branch to this location else. So else, at the label else, you have this instruction, sub instruction, which subtracts R1 from R2 from R1 and puts the result in R node. So that is exactly that is essentially this calculation, f equals g minus h. So you have to do that if the two registers or the two values compared were not equal. So it is in the else part. So you have to put it here. And now if it is not the case, like if they are equal, so you take this branch if they were not equal, but if they are equal, you don't take this branch. Now this is an important point. If you don't take this branch, what it does is, the program does is, it just continues executing the rest of the code. So it does not branch. So branch is not taken. So the PC or the program count is not updated to a different value other than PC plus 4. So it does not branch to another location. Instead, it continues sequentially. So the next instruction we have in line is this add R1, R1, R2. So this instruction is executed if this branch is not taken. Now this what this instruction says is f equals g plus h. This calculation is done using this add instruction. Yeah, so that is done. And once we are done with this addition, we should prevent the program from doing this subtract operation as well. Now, for that, we need to have this bexit branch. Now, say if you did not have this bexit instruction, what happens is it just executes this instruction, and then even if like it does not check whether there's a label given to an instruction or not. So if it is if it like once it is done with this instruction, what it does is it just goes to the next instruction and executes it. So if this bexit was not there, it will execute this sub instruction as well. So else is like this label is not a separate instruction, it's just a label only. So it's just a label given to this instruction, and it does not actually alter the program. So these labels does not alter the program, or it does not add a separate instruction, it's just only a label. So it's actually the address of this instruction. So it is getting resolved to the address of this instruction when the assembler converts this into machine code. So if you are really curious about what happens, yeah. So now once this add is done, you need to make sure that the sub is not performed. So you have to branch to the end of the program. Now at the end of the program, we have another label. We have put it a name. We have put it the name exit. We are the one who are giving this name, so it is not like it does not have to be exit. So you can even put your name here as a label. So exit label is there at the end of the program, so it will perform an unconditional branch to this exit. Okay, we have a question. So when it's good if you ask questions publicly so that others also can see the questions if they also have the same question. So when you're doing it next time, do it. What happens if we add DNA after the add branch not equal after the add? After that, if you add branch not equal after that, then add is going to happen always. Like, so it does not go through this condition checking. So if you compare this and then perform the add instruction without performing the BNE at the first place, then it always will execute add, because with comparison we are just only comparing, so it does not do anything with the branching. So branching actually happens when you execute this branch instruction. Compare is there to compare two values, and if you actually add do the addition and then do the branching, so branching will be done based on the comparison, the last comparison you did. So the last comparison you have done is this comparison. Even if you put BNE just after add, the comparison that will be used for the branch is this comparison. But the downside is that you will do this add operation always without considering without considering the condition to be met. Was it clear? So compare instruction is not doing any branches, so it is there just only for the comparison. Based on the comparison, the branch instruction is the one that performs the real branch. And there's a without using else, can we directly add subpart into that position without using else? Can we directly add subpart into that position? You mean whether it's okay to remove this else label? No. You cannot combine two instructions together. So sub is another instruction. BNE actually is a instruction type. So it's BNE is a BNE is an instruction. It's not maybe like, how do you say? You cannot combine two BNE and sub together and expect it to perform like one single instruction. Actually, there's another instruction type that combines these two. Maybe you are referring to that. So I skip that slide because we need to first discuss this basic form first, and then only we can go to that compact form. So there's actually, so you cannot do it like this, the way you have put like BNE sub. You cannot say it with these keywords. You had to, for that you had to use this version actually. So I was going to come into this one. So this is like a compact way of doing it. It's good that you asked that question, so we can smoothly transition into this place. So for conditional execution, the first form is this one before. So we already have looked at this, how this one works. And then there's another form you can use for conditional executions. And it's a compact version of that. But maybe like there are situations like most of the time, maybe you will not this version because there are limitations. Like you will see that when you are implementing real example, real, like when you are writing solutions for real problems, sometimes this is not possible, but there are like this is possible more maybe. Yeah, this is possible for some scenarios, but there could be scenarios where you are not able to do the conditional execution only using these instructions. So this compact version, what it does is it actually essentially does the same thing that we did with the first assembly code, but in a compact way. The code is compact. So CMP instruction is there, the comparison you had to do, and there's this special type of instruction. Actually, this is a separate type of instruction that performs the addition. So this instruction, we call it add EQ, and this instruction, what it tells is perform this addition if the comparison says that the two registers were equal. So if R3 and R4 were equal, do the addition, do the like like perform this addition described with this instruction. So add EQ R0 R1 R2. So this addition will be performed only if the comparison we did just a while ago says that the two values are equal. And sub NE, maybe this is the equivalent instruction that you can use for the instruction that you suggested. So BNE sub instead. So this one you cannot use BNE sub. You can not use it like that, but you can use it this way. Okay, hope you got the idea. So it's really great that you asked this question beforehand. Sub NE, you can use it like this. So the subtraction is performed if the comparison says it was the two values are not equal. So with this, you can achieve the same task. You can do the same task. No branches, so increases performances, right? So does every instruction has an address in memory so that we can put labels and connect them where we want? Yes, exactly. Every instruction has an address in memory. So instructions are also stored in memory. So this idea I thought maybe is discussed in the lectures. Was discussed because, yeah. Anyway, yeah. The answer to your question is yes. Instructions are also going to be stored in memory, just like they are just like the data is stored, and they are also given each byte in instruction is also given a unique address. That is how byte addressable memory works. And ARM also has ARM, like instruction memory in ARM also has byte addressable has a byte addressable memory. So the instruction formats are given in a table. So all what we discussed earlier has been put here: the data processing, data transfer, and branch instructions. We have talked about this. And So there's an exercise given for you to try out. You have to use sign comparison there, and the skeleton code is given to you. And also there's another example, exercise 4, that also you can try. Since we are running out of time, we will not be able to let you do it now. You can try them, of course, and then ask questions if you have any in the chat. So this is yeah. So exercise 3 and 4 are about if conditions. Compiling if conditions, compiling loop conditions, loop statements is also very similar to the way you do compiling for the if statements, but maybe the way you need to do is a bit different, but the instructions, basic instructions you have to use are going to be the same. So with this, you will understand how loops and if conditions are handled by processors at the lower level using same branch instructions. So this also we'll go through it very quickly because we are running out of time, and the examples you can try out them on your own and let us know if you get into any issues. So this C code here is about a loop. Now what it says is while save I is equal to k, do this incrementing I plus equal to 1. So what it asks is if so it is using actually an array to check these values. So save is an array. The base address of save is in R6, and you are going through this loop to see whether each element in array is equal to k. So if it is equal to k, well, as long as save I is equal to k, you increment the value of I, and then you go to the next element and check whether k that element is equal to k and go ahead, go forward. So you get the idea about that basic loop in C. And I in R3, k in R5. Now compiled ARM code, if you look at it, now here we have two labels, loop and exit. So those labels, they are like the label, the names of these labels, we have given them. You can put any label you want here. And the first instruction, what it does is add R12, R6, R3, LSL hash 2. Now here you can see a shift operation happening, right? So R12, for R12, you are trying to get the address of save I, and the base address of save is stored in stored in R6. So R6. Now R3 contains the value of I. If you know the value of I, you can easily calculate. Now with this instruction, actually what we are trying to do is to find the offset to this ith element in the array. Now offset, we looked at offset. When you are, if you are trying to load data from memory, you need to know the offset to that element, to that particular element you are trying to access. Now this offset is not going to be a constant here. It is a variable. It is going to be a variable. So the offset is a variable offset. I see somebody raising hand. Okay, maybe that's a mistake. So do you have anything now? Do you have anything now? Any other lecture or a 10 to 11 or 10 to maybe 12? If you don't have anything, I can take 5 minutes and finish explaining this. Okay, that's great. If you don't have anything, that's great. Do these labels freed once the compare condition is freed, meaning, so these labels are just they are just labels only. So there's nothing that storing these labels. So labels actually are like place, or how do you say? So that they are used to point to addresses, but when the assembler converts this assembly code into machine code, it actually evaluates or calculates the address corresponding to a technical issue arose and something else. So now we in the middle of explaining somebody's question. Unfortunately, that question is gone because my chat screen got reset. Labels. We were talking about labels. So labels actually, yeah. There's nothing that stores this these labels. So they are just places in the program. So we use them to actually denote several like different places in the program. So for example, if you say loop, it so with the label, the compiler or the assembler can understand what we actually refer to. So these labels are going to be converted into instruction addresses, the address of the instruction that where these instructions are stored in memory. So that conversion between a label to a real address in the memory is done by the assembler. So we use them as labels because it improves the readability, and also before you go and execute this instruction, when you are writing these instructions, you don't actually know where these instructions will be placed in the instruction memory, because it's not just only one program that is going to be executed by a processor. So based on the number of programs that are being executed by the processor, the place in the memory that your program will be placed is going to be different. So at the runtime only, it can calculate the actual address of the place in the memory that this instruction is stored. So if we are talking about physical addresses, so there's like a workaround for this, maybe maybe we can say as a workaround, because at the compiling time also it cannot determine these addresses. So there's something called virtual addresses. So there's a concept called virtual addresses. So virtual addresses actually start from the start of your, so the 0th address is given to the first instruction, and the address 4 is given to the second instruction. Address 8 is given to the third instruction, because each address is going to take 4 bytes in memory. So it's going to take 4 byte space in memory, because one instruction in ARM is of size 32 bits and it is 4 bytes. So that the address corresponding to the label is calculated by the assembler when it does this assembly process. So you don't need to worry about that. And the labels, actually there's nothing that stores these labels. So freeing is not making much sense in this context. And once the compare condition is compare is actually another instruction. So it's just only a separate instruction. It's just like what do you call, it's just like an add or instruction, but the behavior of that is different. It is compare instruction. Actually, it's not compare condition, it's a compare instruction. And once it is done, the only thing that happens is it updates this status register saying the first value was greater than this one, and if it was greater than that one, it will put 1 there in a like, it will set a particular flag in the status register. And if they were equal, then it will set another flag in the status register. So that is how status register works, but I'm not sure whether we'll have enough time to discuss that. If we can get some extra time, maybe we can spend some more time describing how status register works. So for now, for your question, labels, there's nothing that like there's no concept of free labels. So they are just addresses of instructions. So if you try to understand this code, I hope I clear, like I answered question to some extent at least. If not, maybe we can have a chat in the group about that later. We'll now go forward with this compiling of loop statement. The first instruction we were talking about that, and that instruction actually is used to calculate the offset offset of this ith element in memory in the array. So this add instruction, it has this embedded left logical shift left instruction. So with this, what we are doing is R12 is we are going to assign R12 the value of the addition of R6 and R3 left shifted by 2 value. So with this one, actually you can dynamically calculate the offset corresponding to this ith element. So I is stored in R3. Now if you by doing this left shift by 2, what you are actually doing is multiplying by 4. Now we discussed this in brief in the shift operations when we discussed about the shift operations as well. Now shift operations, you can use it to multiply by the power of 2 values, power of 2 values. Okay. So when you do left shift, logical left shift by 1, what it does is it multiplies the value by 2. If you do it 2 times, then you are multiplying the value by 4. So in order to get this offset, now you will understand, like you can write this on a paper and see, and then you are done with calculating the offset, and then that offset is stored in R12. Now R12 is going to contain the address of save I, because you are adding this offset to this R6 base address. So finally, after this execution, R12 is going to contain the address of save I, and you can now load the value to R0. Now for R12 already contains the exact address of the element save I. So you don't need to have an offset there. So that is why we are putting 0 as the offset. So you don't need to put a constant like a different offset here, because we already have calculated the offset and we also already have added the offset to the base address. So you don't need to add another offset here. So that is why we are having #0 here. Now you just like directly take the address stored in R12 and load the value stored in this memory location to R0 register. So that is how R0 is going to be loaded with save Y, and then you perform this compare instruction that compares the R0 and R5. R5 actually contains this value of K, and now you are done with the comparison, and now you are doing this branch instruction, branch not equal exit. Now you are checking whether they were not equal. So if they were not equal, you have to exit this loop, right? So you have to exit this loop if they were not equal. You will be inside this loop as long as these two values are equal. So if it is not equal, you have to branch to exit. Exit is the exit actually is going to be resolved into the address of the last address in this last instruction in this program, which is an empty instruction. Actually, this is like it is like the end of the program. So you can you will jump to exit or the end of the program if these two values were not equal, and if this branch is not taken, you will perform this increment operation. So there you add 1 to R3 #1, that is just going to increment the I value of I by 1. And once you are done with this, so this is just the loop body. So loop body is here. Now, since this is a loop, the important part comes here. You have to branch back to this place, because once you are done with this, you cannot just exit the loop and go to the end of the program. You can exit the loop only when you have found that this condition is not met. But once after you are done with this step, you have to go back to the beginning and start executing the same code again. So we have a branch, we have this label loop. So there you are not checking any condition, you just need to branch always. So that is why we are having B here. So it's a unconditional branch. You perform this unconditional branch back to this place in the program, and then it again goes through these steps, and yeah, you will come to this exit if these two values become unequal. Is it clear?
Excuse me, sir.
So this idea you need to have to do the lab. Was it clear?
Yes, sir. Excuse me, sir.
Yeah. Yes.
If if there is a loop statement again here, sir,
yes.
happens when these statement executes, will it go here or
Yes, yeah, you cannot have actually the same label twice. So maybe it will give you a warning about that. If not, it will go to the first one. So you should avoid those things. You should not have the same label. Just like you will avoid same function name in C. So you should avoid these things. They are not
then
allowed.
to name multiple loop conditions, loop statements in different names, right? Loop one,
Yes,
loop.
exactly. Exactly. Yeah. That is why I told you, you can put any name for a label. So you can even put your name. You don't need to put loop here. You can maybe, who is the rep? Chenal, right? So you can put Chenal here and then Chenal here. So it also will work. So it doesn't matter, right? So these names, all these names are names given by us. They are not standard names. They are not standard keywords, right? These instruction names, they are standard. You have to use them. So they are more like keywords in other languages, but these are not. They are just identifiers given by us. So you can put anything here. So if you want to use multiple loops in your program, of course you have to give different labels for them. Loop 1, loop 2, loop 3, likewise. So it makes much more like sense if you put a sensible name there. So just like it is with other programming languages. For functions, you can put any name. So, but here also you can put any name, but it's good if you put a sensible name. Yeah. I think for the lab exercise, what you have to do is to compile a nested loop into ARM, so that you can carefully do. You have to carefully do that. Now, there's another exercise for you to try out in this tutorial. This is about a basic loop. It's a for loop. It doesn't matter like if it is a for loop or a while loop. That doesn't matter. Like those different types of loops are available only in C. But now you have seen that the basic branch compare instructions you have to use for even both for if and loops. So there are no different like separate constructs available in assembly to perform two of these constructs in other high level languages, if and loops. uh, if you go further, like if you want to compile different types of loops, then they are essentially you will be using the same branch instructions. The same concept you have to used here as well, because at the end in the assembly level it only has these basic operations available. That is it. Now there's a small, like a small introduction, or like a small definition about basic blocks, which is not which might not be really maybe useful when you are doing this lab, but it is useful because it is useful to understand how things happen, and how maybe compilers work. So for when it comes to compilers and things like that, these basic blocks really matter. This is like a definition actually. A basic block is a sequence of instructions with no embedded branches, no branch targets. Right now, actually, a basic block, it's a small concept actually. This a basic block is a set of code lines that does not include branch targets or branch instructions, right? So if you consider a basic block, you cannot have branch. You cannot have a branch instruction except at the end. So at this end, you can have a branch instruction. So it will be branch into somewhere else in the program. Branch target actually is like a label. It's a label actually. Branch target is going to be a label, because a target for a branch is a label that we already have seen. So branch will be branch to a label, and that we, like, more technically we call them branch targets. And at the beginning you can have a branch target. So if you consider a code segment with these properties, then you can call it a basic block. A compiler identifies basic blocks for optimization. So when it comes to compilers, things like compilers, these things become important. The compiler, the first thing it does, the first thing maybe it's not identifying basic blocks, it does other stuff. And one of the important things a compiler does is identifying these basic blocks, because it can do optimizations based on this identification. So an advanced processor can accelerate execution of basic blocks. Okay, so processors, if they are advanced, they can accelerate the execution of basic blocks, because things in a basic block either are executed or not executed at all. So that is how basic blocks work, because there are no branch instructions inside. No, if you have branch instructions, then there's a possibility for a certain set of instructions not to get executed, because based on a branch you will not execute some instructions. But inside a basic block you don't have any branch instructions, so you are sure like it will be executed in its entirety, or it will not get executed at all. So that is how basic blocks work. So for example, here this code segment can be considered a basic block. Now you cannot take this whole thing and call it a basic block, because you have branch instructions inside this block, not only at the end of this code block. So if you consider this code block from add instruction to be this bn instruction, it's going to be a basic block. So that's just a definition and a concept you need to know. You don't need to apply, you will not get a chance to apply that in this lab too, right? Hope that is clear, the idea about how you can compile if and loop conditions. If there's any issue, you can use the chat as well. Here also maybe was it clear? Was it did you understand how you can compile, like, at least some theory parts? Maybe if it is not clear, maybe that those things will be covered in lectures as well. And if you need further clarification, maybe we can arrange a separate time as well. The part where we discussed about how actually you can compile a statement and loop statement in assembly, was it clear? Do you think that you can compile an if or a while statement on your own? So from the 1 or 2 questions that were asked, I felt like you got some idea. You have got it, but I don't know about the others. PC relative address, yeah, that I can explain. Do you have some idea about PC, program counter? Yeah, that's great. Now you know what PC does, right? So PC is storing the current instruction being executed. So or maybe sometimes if you go into fine details, it will be actually stored in the next instruction to be executed. But it knows the current execution. So let's say it's storing the current instruction to be executed, like current instruction that is being executed. So PC it is the address of now this is, we'll say this is the instruction memory. So instruction memory is this, and you have other like more blocks down here, and we'll say this is the address 0x00, and sorry. Hmm. 0x000 x, and the next address is going to be 04, because you all know that this one instruction is 4 bytes. So since the address, like the memory is byte addressable, you have to increment, like the next instruction comes after 4 bytes, and the address of the next instruction is going to be the current instruction plus 4, not plus 1. So here for the next instruction, I'm drawing the instruction blocks here, not the memory blocks, right? So here for the instruction, you will have the encoded instruction of an add instruction, and this could be something else, and this could be something else. So 0x, you have these instructions. Now say your program is now currently executing this 04th instruction, right? So it's executing the 04 instruction, and PC is having that value. So PC is having that value. So more precisely, actually, when the instruction is being executed, it will be stored in the next instruction to be executed, which is 08. But for the sake of simplicity, I'll put it as the current instruction. You can just subtract 1 from that, and then the idea will become clear. So this is PC and it's storing 0x04. That is because it's currently executing the PC and is this one. The class. Now PC is this or 04. It is it is storing currently the the current instruction being executed. Now you all know that each register in all the registers in ARM are 32 bits. So PC is also going to be 32 bits. But unfortunately for this when you have to spare bits, or like when you have to allocate bits for the rest of the instruction here for a branch instruction, so the branch instruction format is given here. The first 8 bits you have to allocate them for other purposes to determine the process, like the processor to understand that it's a branch instruction. So all these formats and all that are encoded here. So it does not use an immediate operand, and also so things like that, and also the yeah, branch type is encoded here. So for other purposes, it has to use these 8 bits, and we are only left with these 24 bits in this instruction to encode the address of the branch target, right? So branch target is actually going to be labels. So labels actually are the names that we have given for instruction addresses. So now, for example, this one here is 0, 12, 12 plus 4 is 16. So this is going to be the 12th location, and for that 12th location, we can give a loop, give a name, a label like loop. So if it is loop, the like the 1, 2, 3, 4, 5, fifth instruction is if we are giving the label loop to the fifth instruction, then at the assembling time, the assembler converts this loop label into an address, and that address will be 16. So the branch instruction will know that the address to be branch, like the address to which it should jump is 16, right? So that address you have to store here. Now, if you have 24 bits, like if you have only 24 bits, you will only be able to jump to addresses that can be represented with 24 bits. So what is the number of addresses, different number of addresses that you can represent with 24 bits? What is the number of addresses? Different number, like 2 to the power 24, yeah. So 2 to the power 24 is the different, like the number of addresses you can address here, right? The number of locations you can address. So 2 to the power 24, it is equal to 16 megabytes. So if you are going to have, yeah, how can it be 2 to the power 32? That is what we are doing here with PC relative addressing. So PC relative addressing, PC is having the current instruction, the address of the current instruction being executed. Now, if you add the branch target or the offset to this PC, what it can do is, now with this one 16, with 16, if you had only 12 to the power 24, your program can only be as large as 16 megabytes, because if it is larger than 16 megabytes, so those instructions that comes after that 16 megabytes are going to have an address that is larger than the address that can be represented with 2 to the power 24. It is going to be a large number which cannot be put here. So 16 megabyte is the maximum you can have. And if you have this one, this setup, like if you are going to get the branch target by adding the address stored here in the branch instruction to the PC value, current PC value. So this could be storing something like 1, and you can add maybe 4. Yeah. For now, let's assume that it's just putting the offset, the byte offset, not the instruction offset. So if it is 4 here, then you can add 4 to this one and get to the next instruction. So maybe one instruction you will not branch, 2 instructions, let's say. So if you want to branch to this instruction, if you want to have a branch instruction here that branches to the instruction 0x12, what is that? 0x12, this is the branch target that's going to be stored here in this branch instruction. So branch to 0x12, right? This might not be the exact way of encoding, but basically it's this. So you have to branch to 12th instruction. This is one way of doing it. If you are going ahead with absolute addressing, you have to put the address here as a absolute address, right? But instead, if you are using PC relative addressing, what you will be putting here is the gap between these two instructions. If you are going ahead with PC relative addressing, you, instead of just putting, you can't edit these text boxes, unfortunately. So let's see. Maybe undo. Instead of putting 0x012, you can put here the 0x08. So if you do this, like this is actually PC relative addressing. So actually this is here after this concept, we are discussing about the about this thing about referring to the number of words instead of bytes. So with that, you will actually be putting here the number 2. That is to say, you need to jump 2 instructions forward. But for now, we'll say we are putting the byte offset, that is 8. So with this, you can put 8 here. So you now get the idea maybe. So this is PC relative addressing. You put the branch target relative to the current PC, and with this you can go up to 16 megabytes from this point. Maybe you can you can jump forward 16 megabytes from this point, and also you can jump backward 16 megabytes from this point. So this address is going to be the offset is going to be a signed number, of course, so that you can jump backward as well. And with that, even if you are at the end of the program, say this is something that is larger than 16 megabytes. This is a program that is larger than 16 megabytes. So still you can branch to targets closer to this one. It could be as far as 16 megabytes away from the current instruction actually, with 2 to the power 24 megabits. So but still everywhere, from everywhere in the code, you can branch to nearby places. Nearby meaning 16 megabytes at max. So it is the idea here. So 2 to the power 32 memory locations, meaning now PC anyway is going to be 2 to the it's going to have 32 bits address, right? All the registers we have in ARM are 32 bits in size. So this is a 32-bit value, even though I have put on 2 hexadecimal digits here. You have to put what the number of hexadecimal digits that will represent a 32-bit number. So you have to divide 32 by 4, which is 8. So 8 digits you have to have. And so with that, the addition result is also going to be a 32-bit number. And the 32-bit number, since you have a 32-bit number as the address, you actually can go for a program as large as 2 to the power 32 bits in size, 32 bytes in size. Now this point is actually having a issue, like a mistake is done here. So it has to be a program as large as 2 to the power 32. Like you can access 2 to the power 32 memory locations, more than 2 to the power 24 memory locations. That's the idea here. Did you get the idea, by the way? PC relative thing is used to go forward and backward from the current PC location, from the current instruction. Still not clear? Okay, great. Clear to somebody else. Yeah. Here in this point, what we are discussing is actually instead of putting the number of bytes here, since we all know that each instruction is going to be of size 4 bytes, that the actual instruction address you can get by multiplying the instruction count by 4. So that you can do easily with hardware. So here, instead of just byte offset, you will be putting instruction offset. So here you will put 2 branch 2 instructions forward. The number 2 you will be putting here, and the hardware, the processor hardware can do this multiplication by 4 and get the actual address, actual offset, byte offset, and it then can add that multiplied value to the current PC to get the absolute address to which it should branch. It is the idea here. Kodagode, are you still having the doubt? Is it clear? Not clear? Clear. Okay. Good. So if you feel like you still have an issue, maybe we can discuss. So in the chat also. Think about it, like look at it again. So I'll be anyway uploading the recording to Fields. Yes, exactly. The PC registry is automatically updated. Automatically meaning you have to have hardware to update that properly. So if there is no branch instruction, what is the increment value? It actually should, like, what is the value that it should increment its value by? So if there's no branch, so it has to go sequentially. Yes, exactly, 4. It has to, like, it has to every time it has to increment its value by 4, because one instruction is going to be of size 4 bytes. So it has to go forward 4 memory locations, 4 byte addressed memory locations to get to the next instruction. So that is happening automatically, like that actually is handled by the hardware. So actually you will be building hardware that can do all these things. You will be building a simple processor in the second part of this course. With Verilog you will be building a simple processor, and you will simulate, and you will actually see how you should handle these things at hardware level. So you are going to get a really good experience. If number of instructions are greater than 16 megabytes, PC gets updated there as well. If number of instructions are greater than 16 megabytes, meaning so you are talking about a solution that does not have PC relative addressing. Okay. Yeah, if it is not a PC relative addressing, then actually you cannot jump to locations larger than 16 megabytes.
You cannot jump, but in the sequence you can keep incrementing 4 by 4 into the next instruction.
Yes, that you can do. Yeah, jump.
But you can't make a jump.
You can make a jump. That is the only case.
PC relative.
Yeah. You can just like keep on incrementing PC because PC still is 32 bits now. So yeah, 2 to the power 32 program you can have, but you can't branch to all the locations in that large program. Hope it was okay. If it is okay, maybe we can wrap it up. Yeah, it actually took more than 40 minutes. Additional 40 minutes. Anyway, since you were here and you asked questions, I stayed here answering your questions. So if you get any further issues or doubts, just use the WhatsApp chat. So we'll answer. Hope that's all.